मेरा ये खो गया है वो हेडअप खो अच्छा पता है नहीं चार्ज अच्छा let's do it.
It's like what we use for the
हाँ I will mute mine. Yes.
I just switch off your speaker also. Yes, never.
So I not maybe I don't join with computer.
Ah, that's fine. That's fine. Make it so now you can show us.
Sound. I just didn't join.
Okay. So, that's one.
Okay. So watching why I was
Changing the slide is not.
oh um,
So,
you will introduce. But तुम्हारे पास है क्या मेरा स्टूडियो?
oh, you have any videos? But you may have one pieces of your first and continuous words. Oh, maybe we can just. No, you gotta read. She was a girl that she can go to use no, I use.
You are fighting to introduce or not?
When the view was not hard. They finally have developed lesson minds. Now you should work. Yeah, you looks like a professor. Yeah.
So
So actually, what was just there? Seminar I can see testing it out for you. But is there a way that the speaker cannot see because ah, I could install some things that make an eyes on the last second. So this so you know
Yes.
That's what you want to drop this element.
What am I working on?
Yes.
Not yet. There was an interesting paper I think we saw that. I can forward it to you. Yesterday, you can get this CW. It's one called for God or our elections. We have done some vital information, then some information, and then I'll forward it. I started for the reviews. So,
Police part of the police. Or you can join.
not very.
Starting party. That would just be lost. Sentence. I mean, it's complicated. When we do it, present in my mind. So on your yes, they could not be that was not that interesting. Pretty well, you know that. I think the thing I read.
Yes.
Yes, समझे I Yes. Day before the science day. So that's why you haven't years. And we have so here PhD in 2009 from the future. So when there are any questions, then please ask. So in 2009, she did a PhD from the Science Institute of Nuclear Physics. Then she went to University of Pune, from Russia. She was there from 2010 to then She was a case researcher at Frankfurt Institute for Advanced Studies, Frankfurt, from 2012 to 2013. In a postdoctoral fellow at the Observable Laboratories. Um, Abnegable. Uh, so, Sierra is researching at NPC. So, I don't know, she works on predicting physics, gravitational waves, and not leverage this.
Okay. So, thank you all for being here. So, the last time I gave a colloquium in Africa was before I joined. So, it's a great pleasure for me to be able to talk about what I have been doing, what my students, my research group has been doing here. So, since this is a colloquium, I will not delve deep into the details of the formalisms that we have been working through. So it's very interesting first from the third perspective. And so what I have to present to you is more or less an overview of what all we have been working on because the discovery of gravitational waves has been basically a game changer for complex astrophysics and the field is really booming in this field. So, I will present you more or less like a qualitative idea of what all we have been exploring in the last 5 years. So, alright. So basically, what we want to do here is to prove fundamental physics with neutron stars. So, why can't we do it here on Earth? That is the question. Good answer. So the answer is that neutron stars provide us a much different perspective of proving fundamental physics than what we can. The reason is that so when we talk about probability physics, what everything around us is made of, usually we turn to some theoretical, some terrestrial things. Like, for example, we look at nuclear experimental data. So here, these plot of the neutron number, proton number, tells you what we usually do with terrestrial experiments. So what we look at ideally is the stable nuclei. But when we also want to look at neutron stars, of course we know that neutron stars are much more rich in neutron than ordinary nuclei that we find here on Earth. So there are a few experiments which look at extremely neutron-rich nuclei. But let me remind you that all these experiments are kind of constrained to densities which are close to nuclear saturation density, which is around 10 to 14 grams per centimeter cube. So this is our limitation. And also that most, like I said, most of these are symmetric in isospin, which means neutron proton number are the same. But however, from many of these observables, so there are observables like time resonances, clear masses, electric dipole polarization, neutron string thickness, which was measured in these PREX experiments. There's a lot going on in nuclear physics. So these give us idea about the properties of matter, which is close to saturation density. So if beyond this, if we do it to explore fundamental physics here on Earth, if so this is also something very attractive. It explores hot and dense matter. So when I talk about dense, it means we can go up to 3 to 4 times that of nuclear densities. And again, matter is also spin symmetric, equal number of neutrons, protons. And also another thing that we see here in these accelerators is strange. So again, this is something that is very peculiar. Mostly everything around us, neutrons, protons are made up of up and down quarks, the lightest quarks. So the standard picture we have from the standard model of particle physics. What we know is that there is strangeness appearing in these particle accelerators, in these Julian collision experiments, which we do not see normally in other experiments. So that means that this kind of dense environment which is also present in neutron a favorable environment for looking for this kind of spaces, which we find for photosynthesis in this area as well. So there are also experiments, hypernuclear experiments, which measure the properties of these hypernuclear, particularly the hyperon potentials. Although the data is much more scarce than in the case of nuclear potentials. So now we turn to complex stars. So these are um, neutron stars, basically are compact objects which are formed at the end evolution of massive stars that end in collective supernova explosion. Why this is very attractive for us in nuclear physics, particularly, is because these are extremely complex. So these have radii of only 10 kilometers, within which you have masses as large as 22 spheres. So that tells us that the density in their interior can go up to even 8 to 10 times that of saturation nuclear density, which is very large set also beyond what we can do best with our terrestrial experiments. And also there are many other extreme properties which complicate and come to that. But I also want to point out that it is extremely cold in general. So they are the temperatures are not higher than 21 to 10 MeV. Magnetic fields can go up to 10 to the 12 to 10 to the 15 Gauss, which means that they can be extremely magnetized, which makes this a very complex thing to study. So, what I'm trying to show here is that neutron stars actually complement our understanding of what we can do with terrestrial experiments. And for that, we look at this diagram, what we call the QCD phase diagram, the diagram of phase diagram of quantum mechanics, which is basically the plot of temperature and function density. So, when we talk about experiments, we are here at saturation density and at high temperatures, we have what we call the lattice QCD experiments. These are basically simulations done on a lattice with temperature low density. And heavy ion collisions probe the phase diagram at finite temperature and finite density. But when we're talking about neutron stars, firstly, these are at so zero temperature. They are at uh, densities which go from 1 to 10 times saturation density. They have finite isospin asymmetry, which means different number of neutrons. So as you can see that these are actually complementing each other, but not so directly. I will tell you how this information can be used. So
Lattice. What is lattice here?
So it's actually a calculation done of QCD. So the idea is that when you have high temperature and low barrier density, you can do the calculations of QCD by replicating them on a lattice with
Still that.
it's like a grid basically. These parameters where the lattice spacing can go to zero and maybe I this is not relevant. So so this actually complicates. So a neutron star is not just a bundle of neutrons, it is much more complicated than that, is what I'm trying to convince you. So here is the cross section of what we think neutron star looks like. So we are spanning a wide range of densities, going from nuclei at the surface to several times neutrons at the saturation density at the core. And we span many different forms of matter, which is why it's so difficult to model it theoretically within the same consistent formalism. Because in the outer crust, we have nuclei embedded in a sea of electrons and also neutrons. But once we go to the crust for phase transition, these nuclei actually under this high pressure start to get deformed into various fine shapes, which are actually pasta shapes because they look like spaghetti and so on, ultimately melting into the core, which is composed mainly of neutrons, which is why it is called a neutron star. But what happens in the inner core is still a mystery because this is where these strange particles start to appear, which means that we can have a or hyperons, strange baryons, you can have meson condensates or deconstruct quark matter, which means quarks which are bound inside protons and neutrons, they can actually become free and form the quarks too instead. So, me. The question is, all this is happening inside the interior of a neutron star. So, how can we actually understand by observing a neutron star from a distance? That is the main challenge of this. So, this is via something what we call the equation of state. Equation of state, like in an ideal gas, means that here it is zero temperature. And what happens is the equation of state actually connects the interior composition with observable properties of the neutron star. So, if you give me any composition like around quartz, so I can reproduce this in the equation of state form. So here you can see that there are different lines on the equation of state form for different composition. These can actually be mapped onto something like the mass radius curve, which is structured by solving TOP equations. So this is kind of like a formula now to translate my inner composition to the state approach. And what I'm trying to do is basically to look for traces of the composition, signatures of whether you can have strange particles in the in some global observable. You can see when telescopes. So basically, neutron stars can be made by zero temperature. Why it is zero temperature? Zero temperature. It can be considered ideally. It can be considered zero temperature because the temperatures are around 1 MeV or lower. So compared to the energies, the chemical potentials, these are much more. So they can be ideally essentially considered zero, except for very high, except for newly born ones or mergers that also come. So as we know, neutron stars were actually discovered serendipitously in radio observation. So now we know that neutron stars can be actually observed throughout the electromagnetic spectrum. And here you see a picture of the crab nebula in different frequencies. So you know that we have a wide spectrum of data for these formations. And these actually give us, we can reduce a large number of colors levels from these features. So now let us start with particularly the mass in the radius because this gives us a lot of information about its interior. So what we want to measure neutron star masses, typically we look at its binary properties. And for that, neutron stars are extremely relativistic, they are compact. So, in addition to the normal Keplerian parameters, we can also measure post Keplerian parameters. And these allow us to measure the component masses in a very accurately. So, here is kind of like a chart of all these masses which are measured for neutron stars. Typically, they are roughly scattered around canonical mass around 1.4 solar mass. But what we are interested more in is the maximum mass that you can measure because in this plot that I showed earlier, if you can put mass limit to your mass radius plot, actually exclude all the equations of state, all the transition which do not satisfy this observance. So mass is very important because it allows us to figure out all the equations of state that cannot satisfy this. So now, in addition to the mass, we need also the radius. So radius measurement is radius one. Yeah. What is that color on the right hand side? Discover. That 2.75 solar mass. What is that? This is from a white dwarf neutron star diagram. I think from all this is 2019. Because I'm worried about the mirror because the information space is a 2.5 is like a lower limit. What object is maybe it is a white dot, not an sorry. So I have there's a lot of complex stuff, but some of them, I mean, they also have some quantity.
All of these masses measured are from the Keplerian or post-Keplerian systems, not from the telescopes.
No, we haven't talked about this. So, Radius measurements. If you have any question, you can ask Arun who is sitting here. So it ask the what's the MI curve they got in the so these are, like I said, so the measurements can come from binary or from related cases. But this it's for a single string. So what I was talking about is that the neutron star mass and radius. So these are still electromagnetic observations that which conventionally has given us information about the neutron structure. So this has been like a something that was uncertain for a long time because of the uncertainties in the modeling that are involved in determining the radius from these observations. But recently, the launch of the nice mission, which is the Neutron Star Interior Composition Explorer mission. So this feature has improved recently because of the pulse profile modeling technique that allows to measure the radii to much higher accuracy, up to 1%. So from cumulatively, so this is what the picture has evolved to. So here you see this row of different equations are staying with different composition. If you translate to masses and radii, again there is a zoo of different curves. So now start putting these limits. So these are all these maximum mass limits, which are ruling out the equations of state which fall below this mass limit. And now on top of that, you add these mass and radius measurements from NASA. And you remember that these satisfy this constraint. And now recently there has been a third measurement of some reanalysis of the previous ones. So these are actually allowing us to filter out all these constraints to give us information about the transfer interior world.
We can read the uh, last one on the right hand side.
Yeah.
So the mass and radius are in two different patches.
Yeah, so these are all, so 1 sigma, 2 sigma mass radius.
For that object.
For that object.
Yes, as a curves. So for that object, you can figure out several curves which are falling below, right?
Which are falling outside this, right? Mostly it is like the very soft and very stiff equations of state, which are in between. There are the ones which are.
And the correct one should it flow through all the different pulses that you measured?
All the different, it should be compatible with all the different observations. So,
Can I ask a question?
Yeah.
Like one question. I think you look at this function, right? So given the radius from multiple mass values. So, for example, what does that physically mean? Like,
yeah, physically, so physically what it means is that, so let's look at one problem here, this snake-like curve. So we can actually compute its stability from the derivative of the pressure with respect to density and actually also studying the radial oscillation. So there are sections which are unstable and sections which are stable. So here this part, so if you are like maybe not in this curve, so for example, carbon diagram. Yeah. Say I look at the very last. Yeah. This one. See, these are at least three stable. Right. So with a radius of 14, if I draw a vertical line, yeah. I have to move a set straight. Yeah. But this is a stable branch, this is not stable. This is known from stability. Then the bottom one is stable. Yeah. So depending on, so this part of this rising part is actually beyond the maximum to be the unstable. So now we come to the exciting part. What can gravitational waves tell us? So like we knew, gravitational waves are a completely new way of looking at compact objects because now they are allowing us to into the interior of objects. And of course, neutron stars being extremely relativistic and compact, they are very important sources of gravitational waves. Not only in binary, so binary is where we expect merge or a collision to neutron stars. But isolated neutron stars. So this is something which has not yet been observed, but it is extremely interesting because it also relates to a number of interior stars. So again, I mean, there has been a lot of effort into actually detecting the gravitational waves, and where collaboration has played an important part in this. And finally, there has been the observation with one miracle observation of the GW170817. We were kind of spoiled because this was the first observation, which was not only gravitational waves, but simultaneously the same event was observed across the electromagnetic uh, paths. So, the Fermi and integral telescopes observed it in gamma rays. Chandra observed it in.
There is a comment from
So, okay. So Chandra observed it in X-rays and all this electromagnetic paths also gave us information about this event. For example, we know that short gamma ray bursts are associated with neutron star module, and that they are also associated with kilonova events. And what is the nucleosynthesis that happens during mergers? We have from one single cube. Fortunately, that will be the only one in the last four observing rounds, but I so what did we learn from this one unit? That actually is a two process. Already what we know is that so if you look at the mergers, there are basically these different phases. So there is the in spiral phase where they are coming together, the actual merger, and then the yin down, the post merger. So during the inspiral phase, what happens is that these component neutron stars they tidally deform like the Sun Earth system and so on. So they tidally the Earth Moon system. They tidally deform each other. And this tidal deformation is actually related to the complex constant or the mass and radius ratio. So this one measurement already gave a lot of interesting information about which parameter space, which equations of state can be ruled out, and also gave a limit to the radii of neutron stars, which are, let's say, completely independent of mass radius relations I talked about earlier. People solutions. So this is a new way now of observing uh, structure properties of neutron stars. So let me come to what how we used this information to constrain interior properties. So what we asked here was, I showed you the QCD phase time. So we have all these terrestrial experiments. We have nuclear experiments, nuclear experiments. So can we combine this multi-messenger astrophysical data information? Can we fold this into the other information and derive important properties of the equation state? So what we did here was this, that in this QCD phase diagram, uh, you have usually calculations, which are, I will explain this in a few slides. So you have nuclear calculations at very low densities. You have heavier collisions at intermediate densities, and these are hot and dense matter. And at high density, you have this multi-messenger astrophysical. So what we did was in a series of rocks, we I'll come to that. So just to say that equations of state actually, so there are different ways of calculating the equations of state. The reason is that you have this extremely dense matter where you have these say neutrons in the neutron state. So this is a many body problem which is extremely difficult to solve. So what people usually do is they look for some kind of microscopic description or an intuitive description. Microscopic is the most rigorous one. So basically, you are calculating order by order these interactions for two nucleon systems, three nucleon, four nucleon, and so on. I think I have to how difficult this is, but this is actually progressed a lot in the last few years. For example, the cybernetic field theory has now become a standard for calculation at very low densities. Because it's a robust tool to calculate the equations of state and of course of pure neutron. We are not talking about restricted media, only pure neutron material, right? But the thing is, there are again different approaches, but there are uncertainties there as well. For example, there are Hartree-Fock models which take into account meson exchange between neutrons. But these again recently people have seen that without three nucleon forces, you cannot sustain two solar mass. And you don't know how to calculate these three nucleon forces. So this is kind of a complicated way of doing things. We do things the smarter way, which is using phenomenology, which means that you have effective density dependent interactions where you have different mesons which basically reproduce your nuclear potential through some observable properties. And that way you can actually explain the different observations, nuclear observations or astrophysical observations. So again, these nuclear interactions. So okay, maybe I will explain. So what we did was basically what we have in the phenomenon of the we have reference density where we have this meson interaction. Like I was saying, these circles represent these different parameters which can be triggered with nuclear empirical data, which is series schools. But these have some uncertainties, right? So this is what I was talking about here in the previous slide. So these uncertainties for nuclear matter is okay, it's better, fairly well known, but very high. There is very scarce data from heavy ion collisions. So that means that our we have also extra additional uncertainties when you are talking to. So anyway, so once you have a Lagrangian, you can calculate the equation of state, and from the equation of state, you can solve your energy momentum tensor and find what is your. Oh, sorry, from the Lagrangian, you can calculate the equation of state. So once you have the equation of state, the idea that we are trying to explain here was that within this equation scheme, we have our nuclear parameter, which is within the uncertainty range that gives you a you construct your equation state and then you calculate using solving tube equations, you get your global observables. You impose your astrophysical data and so much which are actually satisfying this, which means that we can constrain your video. So this technique we used to find the posteriors and also calculated the correlations. Here maybe it's not visible, but basically correlations between nuclear parameters and the astrophysical observations. And we found a lot of interesting things about nuclear properties. Particularly, we found that it is the nucleon effective mass, which is the medium nucleon mass, playing the most important role in determining the nuclear observation. So this was something new that people had not observed before. And we tell you how interesting this is when I come to the next slides. So the same thing again we did for hyperometry. I wanted to ask, are the complete constants in the Lagrangian, are they density dependent or independent? So this also depends on the model. In our case, they are density independent because we have nonlinear couplings in the model. But there can also be density dependent models where your coupling itself varies with density, so you don't need one. So yeah, interesting question. So we repeated the same thing again for hyperplastic, and we found some interesting constraints on the effective nuclear mass, which is the most important part. Heavy ion collision data actually is in contradiction with that of astrophysical data when it comes to nuclear effective masses. We extended this again to quark matter. So in case of quark matter, we had to introduce another model which is called Debarati, where you have additional parameters. These parameters can actually be constrained very well in the case of these constraints I talk about from chiral field theory and heavy ion collisions and very high density. We also use perturbative QC calculations. So we could very something interesting from this study that when we compare our alarm parameter space with those of the densities that are around in the system, we could also predict that only the neutron stars which have a pure, sorry, mixed phase, which means that some part of it is nucleonic and some quark. So these are only allowed by observation and not pure both. So now let's come to some other way of doing.
So the gravitational wave signal has like three phases. Right? Around the time of merger, So you may have equation of state when the neutron stars are separate. But around the time of tidal disruption, your equation of state may change for a bit and then settle.
Yes. So the thing is, I mean, what we call equation of state, we are talking about the cold matter equation of state, which is valid till the time of merger. When you are going to post-merger phase, now you have actually much higher temperatures and out of equilibrium processes. We will talk about it slightly later, but additional effects come on. So equation of state, like what we are talking about, mainly constraining is the nuclear interactions. But of course, other things can come at different stages of it. So,
Someone identifying the equations.
mm,
Now, from equation of state, you go to the matricial state. What confusion is that this is not involved in this spinning and what how does not change? The metric will change depending on those systems. So when they found the initial wave will be from that. Now this metric will change when you have expressions to change.
this I
So
really
this is like a
understand.
local so we can keep forward to that.
You didn't understand it.
So see suppose the cells are spinning.
Yeah, so these are the answers now. Right.
Something called working on the same
Right. So spinning neutron star, yes. So what happens? No, no, there are always complications. So, for example, if you add station in this picture, so we know that central densities can decrease, and there is a limit to how fast neutron stars can. So, I mean, there are things. I mean, right now I'm talking about status. Yeah. You were saying whether it is included in the waveform.
That is what I'm saying.
Waveform.
Waveform is compared with some property.
Right.
So how would you prove if you change that you can change? No, what's the if you be waveform is not true, informative process is same in color. But the method outside the neutral star is different equation. So the thing is that I think the change actually happens at what we call it the only fourth corner equation. The boundary connection and matching of the this change. So all inside the first you worry about the boundary. Why worry? I still what potential are you worrying?
See, for example, when we solve for differential condition,
Problem we get
right?
so whenever we get another area, okay, about the whenever we find a maximum radius, you must then the problem. What are the equations say to find it here? From the chair, looking at the potential past right? It will change the equation, that's what is happening. But here they are talking about loss of struggle. But it's okay, it's 2.5 or some
Effect of numbers. Yeah, that's what I'm saying.
okay. So I the effect of backwards. So initially you can actually have a point when they are sufficiently close, then the tidal has that effect is I think higher and higher. So we must like so let me tell you. Yes, your templates are good. Yes, so that means that the effect will be see, unless you make a
You can add additional connections to your way. But still, at least we are that much higher.
parameter is
Not the dominant.
so they put vertical linear simulation throughput equation of state.
Yes.
Yeah, no, she puts the equation for it. No, it will do something. So there is a personal the shift is not there. The only time there is a shift of the phase by by minor errors will not affect the phase. So
Okay, we can discuss this. So, yeah, so until now, I have been talking about static neutron stars. Of course, there are other effects like rotation, and we know how these can affect neutron stars. So now, so until now, what I talked about is basically I have just used the same coming tidal deformability calculation and used it to combine it with other data to derive, derive some interesting facts about nuclear interactions. Now, isolated transistors. So these could be so ideally. So for example, on Earth, if you want to privately investigate the properties of the center of the Earth, you will look at earthquakes, right? So the same thing is done in astroseismology, in helioseismology, yes. When you look at oscillation, the perturbations from the star and the sun, see what is the interior, how the interior behaves. So the same thing can be done for neutron star astroseismology. The idea is that you can have different oscillation rates. So like earthquakes have also different modes. So you can have oscillation rates, and these are classified depending on the type of restoring force that brings it back to equilibrium. So you have fundamental modes, pressure modes, buoyancy G modes, rotational R modes, and so on. So now the question is, all these oscillation modes actually depend on the interior composition. And if we can observe rotational waves from these non-axis symmetric perturbations, can we say something about the interior properties? So this is a very interesting field to prove properties. So we are first looking at F modes. Okay, so F modes can be expected in dual spiral itself or even in the post-merger oscillation. And they also fall in the 1 to 2 kilohertz range, which is within the sensitivity band, which is why it is transferred for this kind of oscillation. So these are different works done by my students, mainly led by Vikram and Dhruv, and also Nilaksha working on some of these problems now. So what we did was we asked the question: if you have these strange baryons or high currents inside the neutron star interior, how do they affect the F mode oscillation? So here you can see plots of the frequencies of F modes as a function of mass. Solid lines show how they behave if you have only neutrons and how they differ if you have hydrogens. So you can see they do not differ by much, which means that there is uncertainty in the model itself, and it is hard to distinguish them from nuclear. And we also saw how it depends on the effective source, something we found from correlation studies. Again, we did similar correlation studies of the nuclear parameters with F-mode characteristics. And again, we found that it is the effective nuclear mass which was mostly dominant in consuming these F-modes. So this is within this model. So this is something very interesting. And we derived universal relation. So this is already from the very beginning of neutron star astrophysiology. Idea was explored that if we can find some universal relations which can be measured, and then whether we can invert this to find the properties like masses and radius. So earlier it was proposed that these oscillations should be somewhat related to the density of the star. So these kind of oscillation moves were proved. But now, as we also showed in our paper, there are other improved universal relations which are actually independent of the parameters of star, which are scaled relations of the frequency and damping time as a function of compactness and also as a function of this tidal linkage. So these can be used when F nodes are actually observed to derive properties of the neutron star like masses and radii.
So there are people
Yeah.
within the separate these F models.
Right.
You want to confine to the equation of state where you check that it is stable, stable. Is there a particular range of equation of state?
So what is done here is basically we solve so these are general relativity equations. So basically you calculate these oscillation modes, you max and the equation of state information goes into when you're solving these combinations. Is that what you're asking?
Yeah, so that's exactly oscillation is normal.
Yeah, it's not possible.
Positive.
Yeah.
Okay, so it's not pure normal.
These are positive. Well, the frequency not the amplitude. Yes, yes. But
Yeah, I guess I'm not.
I will be
We get the constellation bus. I think I didn't know.
yes, yes.
Yeah, so then you have that.
Right.
Everything.
The amplitude can also be calculated. So amplitude, for example, when they are peaking at the surface, they most peaking at the surface. You can derive them, but we are mainly interested in connecting the F node frequency with the complex structure, which is why we are.
Since these are isolated, so
These are
they scope small one.
these are in isolated.
Oh, I thought you were confident.
So,
When you move on to us, these are
Then you get some nice.
excited in
so
five.
these are non-axis symmetric oscillations. Non-axis symmetric.
I think the frequency is more precisely measured than that. Like, it's a very-
Frequency much more precise is one.
So I think the observation part will be there, right? And some yeah, more effects will be there. I mean,
So scientifically, the linear eigenvalue problem you cannot have amplitude. The linear eigenvalue problem, so you cannot have amplitude.
it's like amplitude cannot be considered.
So this you can calculate that. You have to look at it. Gravitational waves relations, which are in the LIGO map. There are also universal relations connecting tidal information with them. There
Well, inspiring or inspired, be inspired, and you can see.
because it can be executed in the inspired and also in the postmodern isolated.
And you can see it's here. There are some effects in the gravitational waveforms. Uh, if it is excited during inspired, you can see some gravitational waves. I think you will be talking about identical position. Oh, yes. You have by the frequency that comes from single isolated sparkings before.
Remember, also it can be wrong.
So, yeah, sparkings say after what we do. Trading was this last time after the short yes.
Depending on the stability, which is also the question.
The short-lived magnetard or whatever the person short-lived, but even in that you expect
So it would also be stable in passive. I mean, simulations.
I think Shukanto what or there speaks there. There are certain frequency spectrum which were like
Yes, technical, yeah. Let's speak this
in that
force will be. So, right. So, now comes the question is, if the nuclear mass was controlling these F mode characteristics, can we determine this parameter from future observations of F? So, there are already studies in the LIGO collaboration which look for F modes in gravitational wave signatures which are triggered by pulsar glitches. So, if you have glitching pulsar, particularly the Vela pulsar, which is strongly glitching, then when we can determine this parameter, we performed an injection recovery study to show that instead of so a single event, if you have multiple events, for example, multiple glitches of Juna, or you combine them with some other astrophysical observations, you can actually constrain these parameters very well. With particularly, so for A plus sensitivities, you can determine this effective mass up to 3%, and for the next generation telescopes, you can go up percent. So we showed that within this study that yes, so using this interesting fact that the effective nucleon mass controls most relevant study, you can actually recover this. And this is interesting because in nuclear experiments, you cannot measure the effective nuclear mass. It is a dense matter effect. So this is one way of determining this. So other observations. Yeah, other observables here we considered we considered different like in the injection recovery study, we considered like 10 events of Vela, and also what other astrophysical, I think combined with bonus radius. Right, what is
Right.
so this is both for light sensitivity. So this is from the injection recovery study. So basically for LIGO and future telescopes and telescope volume. No, these are from Vela observations. So taking the pulsar energies coming and gravitational energy is so the coming from the glitch. So these are actually yeah. If the glitch excites the so this is one of the ways of being.
There is not much difference between CSRs and unseen things. So I'm wondering why is that? You see the error bars in the when it is confused.
For the equation of state, yes, exactly. No, here actually it does change. So, well, yeah, not so much. If you see the blue band, so this light blue band is A plus and 60, and the blue and red one, so it narrows for us.
After this, they are like very similar, right? Because A plus and LIGO and Einstein telescope
Yeah.
are not much different. Which is good actually. LIGO India can do many things with. Thank you.
No. So, yeah, we also explore some other thing. Maybe I can take this. So again, we asked the same question whether again, like I said, so we considered six parameters, right, for the plot, the previous, right? Yeah. Okay, so which derivative of the static energy? Yeah, so these are so these. So this is not an expansion, but here we are considering up to the slope of the solution. Is there a particular reason? Is it because the higher orders are so you can always add more parameters to your Lagrangian, but these parameters will also have things which will add additional uncertainties to your uh, to the problem. So yeah. So again, you may ask the questions to like she was just asking. So here you can also see that. So you can have different coupling parameters on these different mesons, which within this nonlinear scheme can explain observations that will. Again, the effective mass that was found to be the dominant parameter in our for test modes and structure parameters. You may ask the question whether this is an artifact of this nipple or whether it is a universal. It's actually physical correlation. To test that, recently a study that Rajesh performed. So we compared these observations with a nucleonic metamorph. So this is an alternate model, which actually it does not assume any underlying because it is an expansion of the binding energy in terms of the parameters which are actually measured in nuclear experiments. So when we compared this, we found that these are some of these parameters which are some of the higher order sensitive parameters in the RUF model and compared them with the meta model. And we also, comparing both the models, we found that there is model dependence. And yes, this effective nucleon mass can be measured in this category. So this relativistic mean field phenomenological models. But the nucleonic meta model does not show this correlation with the effective nucleon mass.
They were the previous equation. This capital N is actually what? Sorry, I'm not following everything.
Yeah.
But in the previous equation. So this is like the equation. Yeah. So the N capital N is what? Neutron or something else.
Capital M.
In the equation, capital N.
It's the Lagrangian.
N nucleon. The number of nucleons.
Yes. This you mean this?
Yeah, this capital N in the Lagrangian, the sum and then the
Sums over the nucleons.
Okay, so then my question is, you got two model, one is futuristic radical, one is more or less mean field what follow. So if you take the main field model, why do you need to sum it over to every nucleon? Can you are anyhow subscribe starting with the main field?
No, so the main field, the thing is you have unequal number of neutron protons in the neutron star. Not like in laboratory experiments. I think you're thinking of laboratory experiment when you have same number of neutrons. So when you have large number of neutrons, when you're considering a single neutron in the near field model, you are considering your nucleon is in the background field of the sum of the other. Whereas in protons, it's not the case. The proton number is much more. So here you have also what I'm not showing the other details, like you have chemical equilibrium between these different. So that is the our basic assumption. Yeah. So we also explore smart things. For example, twin stars. So twin star is a concept where you can have, if you have a strong phase transition in your equation state, like here you see a strong phase transition and a mixed phase transition. If you have a strong phase transition, theory predicts that you could actually have a different family of compact star called twin star, and it's called a twin star because it has the same mass as a neutron star and a different radius. So we asked the question whether F modes can actually be used to distinguish between twin stars and normal neutron stars. So I'm not showing the details, but we considered different uncertainties in observations in theory and showed that this is possible to distinguish, but given the current generation of detectors, it is difficult. But the probability is better with the next generation. Um, we also are asking the question, like you said. So when you are talking about mergers, now the equation of state for cold matter is not that big. Because now, in the case of mergers or proton cluster, for newly born cluster, from core collapse supernova, when you have a newly born cluster, you have a foot neutron star. And also the same thing happens when two neutron stars merge post merger. The neutron star is also at very high temperatures. Temperature can go up to 100 degrees. So temperature is not, the effect is not negligible. Magnetic fields also look up, and also you have our chemical equilibrium processes. So this is directed by something called transformation. So what we asked was, if you have FQs which are excited in the first phase, will that change your result? And we also explored this for different stages of evolution of neutron star, how the parameter correlations change, and also how these affect the universe evolutions. So there were some other
Questions, but you see how
interests. So there are these other codes that I was talking about. Until now, we have been talking about F means. There is another oscillation mode, the G means, which are actually sensitive to buoyancy, temperature gradients, composition gradients. So this is very interesting because if you have strange failure or hyperloop, you want to completely change your G. So genes are actually at much lower frequency, but what we found is that if you have high frequency, then there's a very sharp increase in the gene. So this is also a feature. If you observe genes, then you can predict the presence of mass from this kind of observation. Another interesting question is dark matter. So dark matter, as we know, is abundant in the universe, and we also expect that dark matter can be trapped inside neutron stars in different with different methods. But not only that, and there is also another interesting possibility. It's that if you have neutrons decaying via the dark sector, which is somewhat seen in the neutron decay anomaly. So, in that case, if you have your neutrons decaying via the dark sector, and in that case, how do these affect your oscillation? So this is something which we work. Yeah, mostly learning has been leading this kind of progress. So here, so we had a model we um, where we, in addition to the normal fermionic description, you have so basically we don't know the different the particle nature of dark matter is not known. It's basically the dark matter mass and its interactions are not known. So in terms of the dark matter mass and interaction, we parameterize the equation of state, and we varied this parameters and to understand how these can be constrained with observations. Okay. So here we already found that mass measurements of neutron stars can put a limit to the self interaction. strength of dark matter, and also we calculated how this dark matter can affect the oscillation modes.
To assume it to be a fermion or boson entity.
So here here when talking about the dark matter anomaly models, basically the neutron is decaying via a spin half forming, and the light boson is escaping the starlight. So yeah, via the pole. So we found how dark matter affects these oscillation frequencies, and how from different observations we can actually put limits on this on the dark matter particle self interaction and its pass. Another interesting possibility is that you can also have dark stars. So not just until now we were talking about dark matter at its neutron star, but you can also have dark stars, and also these dark stars can be of fermionic or bosonic, and many of them can also be black hole mimics. So when we consider that black holes are merging, so there is also a possibility that these could be dark stars. So how do we distinguish? So we showed that with the help of F modes, you can actually distinguish this exotic compact objects from neutron stars and also. So here we within presuming a particular potential for bosonic massive boson star, we derived scaling relations, and we showed that these scaling relations are actually independent of the dark star parameters. Once you know the scaling parameter, you can calculate f for any particular range, and we showed that these can actually be compared to the neutron star reference to stellar mass black holes and supermassive black holes. And we also extended this to determine from different observations, for example, from cosmological constraints and so on, to put limits on the parameter space. And then to determine what would be the observable parameter space for F loops, how these can be detected within the Lisa band, like Zeno band, and so on.
The reason you call them dark is because there's no coupling with standard modern neutrons.
So these are why we are calling them dark stars.
Yeah.
So because it is just
In general, to be any beyond standard modern boson from black holes. When we say dark, it means dark.
no. So this, I mean, you can have different types of dark stars, right? You can have like axionic and you can have some. So here in this type of model, you have this particular full theory. You have this massive body stars, which within the parameter on showing the
Because I study these objects.
right.
But they're not necessarily, I don't assume necessarily they're part of dark.
Yeah, they are like boson. You can call them boson.
Boson stars. Not necessarily. This is one type of dark stars. Yeah. So I think so. I'll come to the last point. So we also study how interior composition of neutron stars can affect transitions in the neutron star interior and gravitational wave emission. So one interesting point here is that all rotating neutron stars are actually unstable with respect to R modes. So these are rotational waves, and these are the only ways. R modes are actually thought to be one way in which rapidly rotating neutron stars quickly emit gravitational waves and become slowly rotating. Okay, so that's one of the explanations. The way in which this unstable arm can be halted is if you have some viscosity inside the neutron star, and these viscosities actually depend on the interior. So, for example, if you're looking at shear viscosity depends on collisions of particles, neutron, or electron. Whereas if you're considering bulk viscosity, this depends on weak interaction processes like neutron decay and electron rupture. These will these are mostly the common weak processes which produce bulk viscosity, but have some exotic particles like hyperons or quarks. They can additionally give rise to viscosity. And that can change your arc. So it is already known that also that if you have hyperton, there will be a peak in this bulk viscosity, and this will be much higher than the normal viscosity. So this means that if you have tension of gravitational waves via R nodes. For example, here you see the instability window, which is defined by the shear viscosity at low temperature and what viscosity at high temperature. Then you have a neutron star, which is newly born, rapidly rotating. It connects gravitational waves, it slows down, it hits the other end of the instability window. It's where observers expect to observe this rotating constant. So again, like I said, so this depends on the processes which are active, and depending on your interior composition, this instability will change. So if you have a normal neutron star, then you have this black hole. If you have hyperons, so this schematic picture, and it can change your instability window. So we asked the question: if you have dark matter, how will this affect your eventually? So particles are, of course, they are continuous gravitational wave sources. So this is currently something that is being searched, but we have not found evidence of continuous waves from particles. And so we found again, depending on the dark matter processes. This was the first ever investigation of ions from. And we found that depending on the wave process, you can have effects on hormone instability movement, which can be searched for and which can put constraints to your. And yeah, so the weak reaction rates that we were talking about, again, they can be affected by temperature and magnetic field. So we talked about these proto-neutron stars and post-neutron star modules, which are hot and strongly magnetic system. So these will affect your weak rates. So because studied at Chatterjee, and this here we studied for the first time in merger neutron stars, how this is going to affect your energy. So this is something interesting for the community to look at. And this is another new possibility that we suggested is that, like I said, so in general, in addition to this tidal deformation, we can also have tidal heating. But it is considered that for black, so this tidal heating is not zero, and for non-neutron stars, the heating is negative. This is the conventional reason that if you have these exotic components like hadrons in the neutron star, this can lead to this peak in the bulk viscosity, which can result in tidal heating. Actually, depending on the time scale, it can show up in your tidal fields that can be measured gravitational waves. So this is one possibility of this is a sweeping one possibility of looking for strangeness in your neutron star from the phase line observation. So this is my is very last slide. So again, we also proved. So we are currently doing a post-Newtonian calculation of this tidal heating, and we also explored this within a gravitational Raman scattering problem, and also determined at what PN level this effect will come into play. So I think I showed you many different ways in which gravitational waves can help us to prove the interior of neutron stars. In addition to the electromagnetic information that we already have. So currently we are at the fourth observing run of the LIGO-Virgo collaboration. So we have already in 4.3, you can imagine at the end of 4.3 we had detected about 200. So with O4, we have already reached 200 detections. So we are actually getting better at the sensitivities, as you can see from the sensitivity curves. So with the observing run, we are actually getting better at sensitivity. And so we are almost at the end of the O4 observing run. Unfortunately, we have only one observation of binary neutron star. And the that we need to show because that of course like India is planning to join the collaboration which will increase which will improve which will improve the site like vision to many more students. The comes and also showing that this will help. I think it's in the some aspects of the like the graph. So, and of course, the scenario is getting even better with the third generation detectors, which I already mentioned, the Volume Explorer and Einstein telescope. And as you can see here, so this is the O3 and A plus sensitivities, and we're going to increase to CE and ET. You are going to let me answer the question. And what are about the Western state? Australian mission called NEO, which should not particularly underpost for the frequency, but this is not yet found. So, also in the nuclear front, there are many experiments which are currently planned, which will also give us information about nuclear and nuclear reactions. Experiments. The experiment that came facility goes up, slams the middle, um, in this case, up to 4 to 5 times reduction. So this is only going to information to the few CDFA that we have been trying to explore. And so I particularly thank all my students who have contributed to all the work shown here. We thank you all my colleagues here and
There are many questions already. Now, okay.
Yeah. Hi, why the Becky are very interesting with us, Max. Two questions. One a bit more general and philosophical questions. So, why do we expect a single equation of scale for different Newton stars? There's a combination scenario of different Newton stars. Initial conditions affect in some way what spectrum is revealing. Irrespective of how it is informed, the physics of the nucleon interacting with what matter.
right. So you're asking why there should be a sequencing. So I think the answer is that you have I mean, you have seen the aspects. What we're talking about is really asking
Yes, yes. And in fact that as long as we keep pushing the mass cylinder Newton star and keep on ruling out the others, does it mean that the others are not present in the lower mass cases? Because the reason why you are excluding those is because you want to explain all the equations of Newton star with scale. That's right. So why that should be the answer? Because you can spend regarding the condition of forms in Newton star that can have different equations of the range.
so I think the point is that so what current observations what we understand is that when you have so one is having or many one this is that star that can be formed in a particular neutron star sequence. These can be able to be explained within the same within the same way. Currently faced by the model is that when you have additional strange certain additional degrees of freedom, then you get a full pressure. And therefore, you bring down the maximum masses. So currently, most of the massive neutron star observations are moving out a large parameter space of these additional degrees of freedom which tells us a lot about the interactions of these. For example, hyperons, if you want to have hyperon of it's like systems. The only way you can have it, they have very strong touch. So this is actually giving us information about these additional requirements. So I think
Question regarding oscillator. So now there are different modes was discussing. So there are just three instances. Yes. So if one section bring up for example is moves again between inspirators. The dynamic say the next logic and the inspirator. So accordingly notes what are different times
here is so here is a lot of these time scales. So here you maybe something particular with respect to since it's Latin, so time scales. So now, since he wanted to do one, because he may have relevant comments. So, because I saw, and then yeah, I think this is. I have any problem computer will be here. So, will be the price.
Hi. Can you hear me? Can you hear me?
We can hear you. Yeah.
Okay. So I think Debarati somewhere showed about the twin star. So can we do the twin star calculation by using hadronic equation of state? Because you have shown about the by using some quark equation of state somewhere in the slide.
So you said something that two stars.
Yeah, yes, that's slide. So you said it's a fixed mass but different radius. I can also see the hadronic equation of a state which has a mass radius curve. So if you just go for low mass stars, I mean low central density, you can see it's a fixed mass but a different density. Like in your first slide, you shown different mass radius curve where the mass is fixed but the radius is different. So can we do the same calculation by using some hadronic equation of state? Did you understand my question? So let's say you have a just zero point 0.2 solar mass neutron star, which has a fixed mass but different radius. That you can easily calculate it by using hadronic equation of state.
Now, to instruction here, and we shown it the when you are making the scenarios and also the observational bias that goes into calculation in the theory thing. So, yeah, I mean, this.
Uh, so I know this mass radius you observed by using hadronic pathway standards. I just ask it's a low mass neutron star. It's a zero point 0.2 solar mass. That I can just calculate it by using simple hadronic equation of state. Where in the lower you can see it's a zero point 0.5 solar mass, but it's a different radius. So if you just go to the first or second slide, you have different mass radius curve. Yeah. So next slide. Yeah, this slide. Yes, this slide. You can see it's a zero point 0.2 mass, solar mass. You have a constant mass, but it's a different radius.
Why two solar mass?
Yeah, so it's a here also the mass is constant, but it's a different radius. Can we say it's a twin mass neutron star? Can we extract from here?
It's not an issue. It's you guys said discuss yes. So wait, is it that? But if you did only question related to this one question, yeah.
Y-
That actually maybe you refer to our paper because we have detailed discussion about it and you got to the other pages. Yes. So, we investigated the Argon calculations. Right. But has we cast it out in fact the region of consideration or condition approximation. which is being used as a basis for calculating our nodes, had some more traits, like for example, shape corrections, etc. So, theoretical aspects of why such are non-fictional was that irrespective of the results to relations of sources of continuous speed are written that people are actually scrutinizing other aspects because most of the time people take like a very canonical neutron star with some given radius and context. But now some regular results similar so people are actually scrutinizing. Maybe we can discuss more.
Now, two questions. Should we maybe question about this like possibilities space? I think all the feelings is why first of all, why are the releases so broad compared to the process limits and how exactly they can be improved? Because there's a lot of scatter in the horizontal direction,
Right. So,
much in the vertical way.
right.
So how can maximum access can be achieved?
So, so these have been very stated. This development happened as with pulse profile in Maxwell, where basically you're looking at a test. And you can see the output even when they're behind and that tells you what the result is. So, so more than the mass, like I was saying, there is mathematical. But then, so gravitational wave information. This is sustainability is related to the radius. So this actually is giving an independent way of and a lot of the investments will actually they are in contradiction to either. So this is an interesting one. Investments actually no, measurements of time to deformability. You can have maybe lower in the radius and that will constrain this better. Because nicely, I think I was showing this plot where nicely nicely experience. So the there was a very narrow and very small data and very same the need for but I think in addition we do now having gravitational wave directly from living elements. So this is often in contribution with the other one. So
I think we should have a total service.
I think it's
I mean, that thing looks interesting. That
10%.
10. Okay. Yeah, sure.
So the traditional matter physics, the core, right? Compared to dark matter stuff. They have see a specific real signatures because in addition to the theoretical signal, the see real signature. Can we specifically identify that this type of star? Or we cannot differentiate between them. So
Electromagnetic signature, I think you're talking about the post merger. So post merger until now, so GW170117, for example, you have this like blue color the the time of collapse of the number. So we have some instances until say last so that means that if the stable model it lasted way. So that is the correct equation because not all equations of state with the with matter can actually sustain a stable infrastructure with a particular mass to one. So that is the only thing we have at it. When you compare with the simulations, because
nature of are we can
So there were lines, so I think I don't have that third here, but there were so on BLT, there were some particular lines which tell you that
so that is
but also like I said, this is a colloquium, so I wanted to give an overview, but you can look at the papers and if you have any questions, you can reach me. I skipped along with